Good morning to everyone. Myself, I Bharat. Today, I am here to present my tech talk presentation. Today, my topic is discuss the design challenges of large-scale PV power plant. Introduction: large-scale PV projects require integrated planning across site, electrical, mechanical, and regulatory domains. Early-stage decisions drive lifetime performance, cost, and risk. Prototypes, resources assessment, layout, efficient, and grid compiled to maximize ROI. Site assessment, resource variability. Assessment integrated solid rated and seasonal validation to predict energy yield. Use high resolution solar data and satellite validation to reduce production uncertainty and inform financial models. Land use constraints. Map topology, land ownership, and complete uses. Design around slope drainage and access to minimize earthworms and permitting delays while protecting project footprint. Environmental permitting evaluates habits, wetlands, and cultural resource early. Develop mitigation plans and stakeholders engagement to rescue, permit, and avoid cost reducing or integration. Layout optimization, row spacing and title. Optimize tilt and row spacing for altitude model type and expected soling. Balance energy yield against land cost and construction complexity to maximize LCOE reductions. Shading analysis. Performance dynamic shading simulations across design life to prevent performance losses. Incorporate straight layout and inverter placement to mitigate mismatch and maintain dispatchability. Access and drainage. Design access roads to support construction and OM while minimizing iron distribution. Implement drainage canals or culverts to prevent pooling and module with washouts. Prioritize durability access and permittable solutions to reduce maintenance and erosion risk. Electrical design. Collection system. Select cable sizing and routing to minimize losses and installing cost. Plan substations, locations, and combiner layouts for efficient conductor runs and reduced voltage drops while allowing safe maintenance access. Transformers and inverter sizing. Match inverter topology and transformer capacities to array output and grid requirements. Consider redundancy and thermal performance to optimize availability and limit culpability risk during peak production. Grid interconnection. Access points of interconnection capacity protection schemes for interconnected studies area. Coordinate with the utility of timing grid upgrades and ancillary service optimizations to ensure seamless coming OEM and reliability. Asset monitoring deploy SCADA and string level monitoring for fast fault detection and performance analysis. Use predictive analysis to automate investigations and maintain high uptime. Degradation and cleaning. Model module degradation and soil rates to define cleaning schedules and warranty claims, balance water use, cleaning frequencies, and yield gains to minimize operational cost and sustain energy up to output. Spare part strategies. Make critical spare inventory for inverters, transformers, and trackers based on failure rates. Establish supply arrangements on site kits to reduce downtime and support timely repairs. Resource variability. Access integrates soil rated and seasonal variability to predict energy yield. Use high resolution solar data and satellite validation to reduce production uncertainty and inform financial models. Land use constraints. Map topology, land ownership, and competing uses. Design around slope drainage and access to minimize earthworms and permitting delays while protecting project footprints. Environmental permitting evaluates habits, waterlands, and cultural resources area. Develop mitigation plans and stakeholders' engagement to secure permits and avoid cost litigation through integration. Layout optimization, row spacing, and optimize tilt and row spacing for altitude, module type, and expected soiling. Balance energy yield against land cost and construction complexity to maximize LCOE reductions. Shading analysis. Perform dynamic shading simulations across design life to prevent performance losses. Incorporate straight layout and inverter placements to mitigate mismatch and maintain dispatchability. Access and drainage. Design access routes to support construction and OM while minimizing and lash distribution. Implement drainage canals and cultures to prevent pooling and module washouts. Prioritize durable access and permittable solutions to reduce maintenance and erosion risk. Electrical design. Connection system. Select cable sizing and routing to minimize losses and installation cost. Plan sustainability locations and combine layouts of efficient conductor runs and reduced voltage drops while allowing safe maintenance access. Transformers and inverter sizing. Match inverter topology and transformer capacities to array output and grid requirements. Consider boundary and thermal performance to optimize availability and limit catalyzation risk during peak production. Grid interconnection. Access points of interconnection capacity. Production schemes and interconnection studies early. Coordinate with utility on time. Grid upgrades and ancillary service are available to ensure seamless commissioning. O&M and reliability. Asset monitoring. Deploy SCADA and setting level monitoring for faults detection and performance analysis. Use predictive analysis to prioritize investments and maintain high uptime. Degradation and cleaning. Model module degradation and solid rates to define cleaning schedules and warranty claims. Balance water use, cleaning frequency, and yield gains to minimize operation costs and sustain energy output. Spare part strategy. Maintain critical spare inventory for inverters, transformers, and trackers based on failure rates. Establish supplier arrangements on risk side tickets to reduce downtime and support timely repairs. Conclusion. Early integrated decision across sites, electrical and OM domains determines project success. Focus on data-driven decision, stakeholders, conditions, and resilient operations to minimize energy yield and optimizing life cycle cost. Thank you.